welcome back to the channel. So today we'll be looking at 9702 May-June 2020 variant 22, and specifically we'll be looking at question 4. Okay, so let's start with A. They ask you to state the difference between progressive waves and stationary waves in terms of the transfer of energy along the wave. So actually the answer is already in the question itself. So by progressive wave, we know it's progressing, it's traveling. So ideally, progressive wave will transfer energy. Whereas stationary wave is basically not moving because it's like standing waves, right? So if you're not moving, that means you do not transfer energy, right? So yeah, that is the answer for the question. So progressive wave transfer energy while let me rewrite my while stationary waves do not transfer energy. So this question is actually very nice to you. Actually, they specifically told you like in terms of transfer of energy, so don't miss out this 1 mark. Okay, moving on to B. A progressive wave travels from left to right along a stretched string. Figure 4.1 shows part of the string at one instant. So this is basically a progressive wave, and this is the direction of wave travel. Okay, P, Q, and R are 3 different points on the string. The distance between P and R is 0.48. The wave has a period of 0.02 seconds. So that means T equals to 0.02 seconds. That means it takes 0.02 seconds to complete one cycle or one full wavelength. So use figure 4.1 to determine the wavelength of the wave. Okay, so wavelength, we know that it's actually the distance from either crest to crest or throw to throw. So here we can use throw to throw. This is one wavelength. This is one wavelength. And throw to another throw. Okay, I think I'm gonna extend the wave a bit so that we can see. Okay, so throw to another throw is another wavelength. Okay, so 0.48 stops exactly at half of the wavelength, because this entire thing is lambda, right? So half of it is lambda over 2. So that means lambda plus lambda over 2 is equal to 0.48. Okay, so you compute your lambda, you get lambda equals to 0.32 meters. Yeah, so the answer is 0.32. Okay, now moving on to Roman 2. Calculate the speed of the wave. So we know that we have a formula V equals to F lambda, right? So V equals to, frequency is 1 over period, and we know period is 0.02 seconds. Therefore, we can say it's 1 over 0.02. Make sure you check your unit, okay? Here it's in seconds, so I can safely use. If let's say it's millisecond, make sure you times 10 to the power of negative 3. Okay. Lambda is 0.32, what we have found in Roman 1. And when we calculate this, we will get 16 meter per second. So 16. Also remember to check your significant figure also, yeah? Make sure it's minimum 2 significant figures. And Roman 3, determine the phase difference between points Q and R. Okay, where is Q? Oh, Q is here. Q is here and R is here. So phase difference is basically the distance between Q and R divided by wavelength times by 360 degrees, because the answer they want in degrees. If they didn't give units, then you can either times 2 pi in radians or 360 degrees. But since they give units, so we have to times by 360 degrees. So the distance from Q to R is basically, okay, this one is one wavelength, right? One wavelength. Then plus this, it's quarter of a wavelength. So we know 0.32 is one wavelength. So what we can do is 0.32 plus 0.32 over 4. Why over 4? Because this is quarter, right? From Q to R, this is one wavelength, then we have a quarter. So when you do this, you will get, wait, let me take my calculator. Divide 4, you'll get 0.40 meters. So you want to know what's the phase difference? Basically, the distance between points Q and R divided by a wavelength, which is 0.32, comes by 360 degrees, and you will get 450 degrees. That is your answer. This 450 degrees basically means it has gone 2 cycles. But if let's say you want to reduce it to 1 cycle, your answer can also be 90 degrees lah. Yeah. But since this is your calculation, you can just stick to 450 degrees. Alright, let's move on to Roman 4. Figure 4.1 shows the position of the string at time t equals to 0, okay? Describe how the displacement of point Q on the string varies with time from t equals to 0 to t equals to 0.010 seconds. Okay, so if you realize 0.010 second is actually half of the period. Why? Because they have mentioned here that the wave has a period of 0.02 seconds. And half of the period, isn't it 0.01 seconds? Right, so they are asking you how does point Q varies within half a cycle. Another thing to take note is, what is the time after quarter cycle? That means what is the quarter period value, which is 0.005 seconds. Okay, so from here, we know that when Q is at this point, the wave was at time t equals to 0. The time was t equals to 0. Why? Because they mentioned at this point, figure 4.1 shows the position of the string at time t equals to 0. Okay. Now, the next thing you should ask yourself is, how is this point going to move? Whether it's going to move up or down or left to right. Point Q is going to move up to down because this is a string and this is a transverse wave. So transverse wave has stated that the particles move up and down. If this was sound wave, that means it is a longitudinal wave, therefore the particle will move left to right. Whether it moves left to right, up or down, both of it will give you a different answer. So it's important to know what is the type of waves you are dealing with so that you know where the particle is going to move, if they move up and down or left to right. So now we have concluded that it's moving up to down because it is a transverse wave and it's a string. Okay, settle. Now, whether it moves up first or whether it moves down first. So based on the picture here, Q is supposed to move downward first. Why? Okay, so let me draw. Okay, let me just trace this wave here, then I'll move it. Okay, so let's say after a certain time, your wave is going to move this side. Wait, it's not moving. It's going to move this side. So you realize point Q is moving down, right? Then probably after another few seconds, point Q moves here, right? Then now probably after 0.005 seconds, which is after a quarter cycle, point Q is probably at the lowest point already, which is here. So at time t equals to 0.005 seconds, Q has a maximum downward displacement. It has moved a quarter cycle. Now, what happens as it moves towards 0.01 seconds? your wave is going to move to the right, right? Realize what happened to the position of Q? It's going up. Here. Now let me move it again. It's going up back. Here. This is your Q, right? So from down here just now, it goes up here, then it goes up here. So now at t equals to 0.01 seconds, it's going to go back to its initial position. So basically at t equals to 0.01 seconds, point Q returns back to its initial position and half a cycle is completed. So it's best if you could draw. Of course in exam you can't move like this, right? It's you're in a paper, using paper, but I would suggest you perhaps to draw it, so that draw the waves, so that you can realize it, how it moves. But if you can visualize it, sure, you don't have to draw it, of course. This is just me explaining to you. So it's important to know whether the particle is moving downward or upward first. So let me give you another example. Okay, this is not asked by the question, but I'm just going to frankly give you another example. Let's talk about this point. Let's name this probably M. So what do you think will happen to M? Will it move downward first or will it move upward first? Ideally, it's supposed to move upward first. So if I were to shift the graph to the right, to the right, because the wave is traveling to the right, realize what happened to point M? It's moving up. Then if I shift even more, it's moving up. So in this case, point M moves up. In the previous case, of the case of Q, point Q, okay, let me move back. Initially it was here. Then when the wave travels to the right, it moves down. If I put it even further, this is probably at 0.005 seconds, it's at maximum displacement. Then moves again, the waves moves again. Realize your point is going up back. Then I move even more. This is already at t equals 0.01 seconds. Q returns back to its original position. So that is why our first point should be point Q has a maximum downward, it's very crucial to mention downward, displacement at t equals to 0.005 seconds, which is half a cycle. Then point Q returns to its original position at t equals to 0.01 seconds. Because first it came down first, reaches a maximum downward displacement, then another quarter cycle, it goes back up here. Right, so basically, in simple words, the process of the motion of point Q is it goes down, then it goes back up here. Yep. Moving on to C, a stationary wave is formed on a different string that is stretched between two fixed points, X and Y. A stationary wave, okay. Figure 4.2 shows the position of the string when each point is at its maximum displacement. Roman 1, explain what is meant by node of a stationary wave. So, a node of a stationary wave is actually a position where it is zero amplitude. So, definitions, make sure you memorize before you go inside your exam hall. Don't waste all this 1 marks, okay? Make sure you score all the definition marks. State the number of anti-nodes of the wave. Okay, let's label. This is node. This is also a node. This is also a node. Zero amplitude, right? This is antinode. Antinode. Antinode is always at maximum amplitude. So from what I have annotated on the diagram, we have two antinodes. I know the answer scheme wrote 2. But here's the thing. They always say leave answer in 2 significant figure, right? So 2 significant figure, they specifically explicitly mention is for your calculations. But it wouldn't harm you to write 2.0 lah. I don't think it's wrong either. Yeah. State the phase difference between points W and Z on the string. Okay, where is W? Oh, W is here. Okay, let me erase this. So W is here, Z is here. So now the next thing W is going to do is W is going to go down and Z is going to go up. Am I right? So realize they are moving opposite to each other. That means they are not in phase. They are in anti-phase. In phase means both of them move up together. For example, if I label a point here, let's say Z. So if they ask what is the phase difference between point W and Z on the string, you need to calculate it lah. That means they'll give you more information on it. But both of them, W and Z, will be in phase, because if W moves down, Z will move down. And when Z moves up, W will move up as well. But in this case, the Z is now here. So when W moves down, Z is moving up. Shows that it is anti-phase. Anti-phase means 180 degrees or pi radian. Since the unit they give you in degrees, make sure you write 180 degrees. Always check your unit here. Don't go and write pi here. It's actually wrong, even though ideally it's correct. But since the unit is degrees, make sure you write 180. So since it's anti-phase, you write 180. Okay. Now Roman 4. A new stationary wave is now formed on the string. Okay. A new wave has a frequency that is half of the frequency of the wave shown in figure 4.2. Half. Okay. The speed of the wave is unchanged. Alright. On figure 4.3, draw a position of the string for this new wave when each point is at its maximum displacement. Alright, okay, let's go back to figure 4.2. Let me erase this entire thing first. Okay. You know this figure 4.2 gives you a full wavelength, which is one complete wavelength. Okay. And if you realize, if you manage to notice this, this is actually second harmonic. Or you want to call it first overtone. Second harmonic of the fundamental frequency. So ideally, if this is second harmonic, that means your frequency is 2f0, 2 times the fundamental frequency. So if 2f0, 2 times the fundamental frequency, gives you lambda, which is one complete wavelength, now they say it is half the frequency. They want it to be half. So half the frequency means goes back to the fundamental frequency, which is the first harmonic. So 2f gives you lambda, 1f will give you half the lambda. So that means you have to draw only only half a lambda here. Let me redraw this again. Half a lambda here. Okay, another way to approach this question is using the term length. So let's say you didn't know that this was second harmonic, or you didn't know this was first overtone. It's okay, no problem. There's actually an alternative to it. So let's say I label the distance from x to y to have length L. And we know from the diagram it is a one complete wavelength. So we can safely say that lambda equals to length. One wavelength is equals to the distance from x to y, which is the length L. Okay, keep that in mind. And now, since you don't know this is second harmonic or first overtone, you're probably going to assume that this figure 4.2 has a frequency f. Okay. Now, in Roman 4, they say that this new wave has now half the frequency. So, the wave in figure 4.3 will have half the frequency. Now, using the formula v equals to f lambda, given the fact that the speed of the wave is unchanged, we can say that f is inversely proportional to lambda. So let's use the ratio method. Now, we want to know how much wavelength you have to draw, whether you have to draw half, whether you have to draw full, or 2 wavelengths, what are you going to do? So let's make wavelength on the left hand side. So a new wavelength divided by old equals to, since it's inversely proportional, so the frequency, old frequency has to be the opposite of the old wavelength, and we have new frequency. Okay, lambda new is what we are going to find. Old wavelength, we know it is L, right? Because we have set lambda equals to L, which is the old value, L. And the old frequency is F, the new frequency is F over 2. So now you do the math. Okay, I'm going to go at this side, right? So lambda new equals to 2L. Okay. If you realize, they also label this as X and Y. That means if the X and Y here has a distance of L, definitely the X and Y here must also have a distance of L. But here now they say the new wavelength has the length of 2L. So that means, if I erase this at the side here, if I were to draw, there must be another similar X and Y here with the length L, and this will be your new wavelength, because they say new wavelength is 2L. Now since they only give you L, which is half of it, so you only draw half the wavelength. Okay, yeah, so this is another way to approach this question. So if let's say you remember this was second harmonic, sure, go ahead, proceed with this. If let's say you forgot, no worries, let's use what they give. They give speed of the wave is unchanged. We can use the fact that frequency is inversely proportional to wavelength, and you'll still get your answer. Make sure you know how to interpret the question and your formula properly. You should be able to get your answer. Okay, so that's all for today's video. Today we talked a lot about progressive wave as well as stationary wave. So I hope this video helps you in your revision for waves chapter. And that's all from me today. I'll see you in the next one.